How does a person determine an object's displacement given the object's velocity versus time graph? This is the question that students will explore in this investigation, 4B, a model for accelerated motion. In this investigation, students collect velocity time data using the smart cart on an inclined track and then establish relationships between the area under the accelerating cart's velocity time graph and its displacement. Leading up to this investigation, students should understand that an object's displacement is equal to its velocity multiplied by the change in time only if the object's velocity is constant. Students should also know that the equation velocity multiplied by time is the same as the equation used to calculate the area under a flat velocity versus time curve. The relationship established in this investigation is later used by students to build the equation for motion that includes acceleration and position. For this investigation, each student group will need a smart cart, a dynamics track with feet, an end stop for the track, and a couple of textbooks to incline the track. Students should assemble their equipment like this, with the end stop attached to the decline end of the track and the plunger end of the cart facing the end stop. In this setup, students use the plunger on the cart to launch it up the track. The inclined track causes the cart to experience constant acceleration, which will make it roll up and down, bouncing off the end stop at the bottom. Students record position and velocity data as the cart rolls up and down, and then use information from that data to establish the relationship of interest. Once the equipment is assembled, each group will open the experiment file 4B models accelerated motion. And then connect their smart cart using Bluetooth. Groups are now ready to begin recording data. For part 1 of the investigation, place the cart at the bottom of the track with the plunger pressed in 2 clicks. Start recording data and then tap the plunger trigger to launch the cart up the track. Students should try and stop recording data just as the cart starts rolling back down the track. Like so. Because the acceleration of the cart is constant, the position data should be curved and the velocity data should show a straight line sloped downward. Students should sketch a copy of their position time and velocity time graphs in their handouts and then use the tools in SparkView to find 3 things: the area under the velocity time graph, the final position of the cart, and also the cart's displacement. To find the area under the velocity time curve, first we have to make sure we have the correct data selected in SparkView. And because I want to analyze my velocity data, I want to make sure it's selected. It's the green data, and the green data is selected. Then I activate the statistics tool and select area. To find the cart's final position, again, make sure the correct data is selected. In this case, I want to select my position data, which is purple. I'll select it in the legend. And then I'll activate the coordinates tool and drag it to the very last or final position data point. Students then record those values in their handout. And for us, the area under our velocity time curve was 0.484. 0.484, and that's in meters. And our final position was 0.485, and that's also in meters. And now for displacement, because the initial position of the cart was 0, the cart's final position is equal to its displacement. So this is also 0.485 meters. For part 2, students repeat the same procedure as part 1, except instead of stopping data collection before the cart rolls back down the track, students record about 8 seconds of data as the cart bounces off the end stop. Students then find the area under their new velocity time graph and the displacement of the cart, and then record those values in the handout. So for our values, I'll make sure that my velocity data is selected and then activate the area tool again. and then make sure my position data is selected, and then activate the coordinates tool and drag it to the final position data point. Okay, and then let me record these in the handout. So the area under our velocity time graph is 0.045, 0.045, that's in meters. And then our displacement, again, is equal to our final position, which is 0.045. And that's also in meters. Students analyze their data from both parts by examining the values for the area under their velocity time curve and the corresponding displacements. In both part 1 and part 2, these two values should be approximately equal to each other, like we see here. This implies that the displacement of the cart is equal to the area under its velocity time curve. In both parts of this investigation, the cart's motion was almost uniform. At the very end of the investigation, students are asked to explore whether the same relationship exists when the motion is non-uniform. Students should follow the same procedure as in parts 1 and 2, except this time use their hand to roll the cart up and down the track in a non-uniform way. Students will find that the same relationship exists between the area under the velocity time curve and the cart's displacement, even if the motion is non-uniform.